Hello and welcome to the Null channel. This is a place where we learn about software engineering together. I'm here today to report on some of the most bombastic news to rock the software engineering industry. AWS has in fact stopped using microservices for all of their internal services. In fact, from this single blog post that we have here, we can infer that all of AWS's services are now moving to a single monolith in a single code base that is deployed to a single machine. That's right, you heard it first here. All 30,000 AWS engineers work on the same code base now. Well, hold up. Maybe that's not all true, but they started using monoliths, right? I mean, they did release a blog saying so, correct? Well, unfortunately, if you've been reading the headlines from places like Medium or the Newsstack or many other places, and even unfortunately here on YouTube, you might read headlines that say something like the return of the monolith, or the monolith strikes back, and the death of serverless. Well, thankfully for you all, and thankfully for the internet, you all have me. That sounded way more narcissistic than I intended it to. But before we move forward here, I don't have any inside knowledge. Just the blog posts they themselves released. So I'm not coming from any point that you yourself could not obtain this information. Now, before we get into the blog and how I think a lot of people got this wrong, I mean, I even think AWS got it wrong in their blog post. Let's jump outside into the great outdoors and talk about the real lesson we can learn from this blog post. And yes, I am going to help you learn software engineering by cutting the grass. If you never thought about how cutting grass could make you a better software engineer, well, today you might just learn. After we learn about how software engineering and how this blog post specifically relates to cutting the grass, we'll jump back in here into the lab and go over the article paragraph by paragraph to understand just what happened and why AWS, in fact, still uses microservices by their own standard and admission. So let me ask you something. Can you cut the grass with this pair of household scissors? So the fact is, we can in fact use these scissors to cut grass, and we can do it quite well. It cuts grass really well. The scissors don't complain, and really they're a fantastic brand of scissors. But that's not actually the point. If our goal is to mow this grassy field that is surrounding us, these scissors will never get the job done, or will they? Could we actually scale cutting the grass with those scissors? And the fact of the matter is, we could. Scissors scale very similar to microservices. All you have to do is add more people. We can keep adding scissors, and we can keep scaling our service that way. That's right. The scissors are a microservice. So we could actually cut this field in maybe 10 minutes. It might need more than 100, 200, 300 people to do it, but we could do it. Now, is that cost effective? No, it's not. A service architecture isn't anything special. It's not something that you can't obtain. It's something that large companies do to help manage themselves. It's a people management over architecture of your application. And this is fine, and this can be useful if you're worried or dealing with that type of scale. So what I want to emphasize is the real lesson we can learn here is to pick the right tool for the job. And I think that's the biggest thing. The other thing, like the secondary side note that we could learn from this, is to understand the cost of transferring your data around in applications. And this is something I have notoriously said. The cost to transfer state is expensive. So if you're transferring state from application to application, that might be a sign that you have a microlith and not a microservice. Now, the more specific a tool gets, the more focused it gets on one thing, usually the better it is at that one thing. Take a lawnmower, for instance. It really only cuts grass, but it cuts grass pretty well. These scissors, for example, are kind of a multi-purpose tool. They cut pretty much anything, but to be honest, they're not that good at it. If you wanted to cut paper in a straight line, there's actually better tools for it than these scissors. That's right. There are things that will cut paper in a nice straight line for you that is quite fantastic. So let's hop back into the lab and dissect this article just a little bit better and understand what really went wrong, what really happened, and what we can learn from it as engineers. All right, back here in the lab. I guess the TLDR is just this. The only real thing I could gather from the AWS blog was use the right tool for the job. And as it turns out, step functions in AWS's use case were not the right tool for the job. Second lesson to learn here is that microliths are in fact a bad architecture design in almost all cases. Like I have talked about many times before, microliths cause a lot of issues and solve almost no issues at all. Just like with mowing the grass, these scissors were just not the right tool for the job that we were trying to do, which was cutting the grass. That does not mean in any way that these scissors are a bad tool or not worth having in your house. It didn't even mean that we could not scale horizontally. We could deploy hundreds of thousands of these scissor-wielding mowers. It sounds a little dangerous though, but let's look at the article and see what we can't glean from it. The first few paragraphs, these first three itself, are really just stating that they created a tool that was never intended to scale, and it all seems pretty reasonable, talking about how they were trying to monitor the quality of their streaming service. And really, it seemed like it was a tool one person used, or maybe a couple people, and they would just use it on a single stream at a time. There was no need for it to scale. This is okay. Not every tool has to be designed to scale from the start. You can make something scale once it has a reason to scale. This is okay. So then they described the initial version of their service, talking about how it consisted of distributed components. That sounds fine, sounds like it should scale, and it uses AWS step function. We're going to talk more about those in just a second. And that it was an internal QA tool initially. The first issue to note here was the expense. The two most expensive operations in terms of cost were the orchestration workflow when data passed between distributed components. That's actually two things. It was the orchestration and data being passed between components. Now, here is my first nit with this article. They talk about distributed system overhead. I will be the first to tell you that a good distributed system is going to cost you a bit more than a proper monolith. But the things they point out here are in fact microlith issues, not distributed systems overhead. If you would like a video on the overhead of a good distributed system versus that of a monolith, please let me know. I would be happy to talk on the topic. So there are actually two different scaling issues listed here, two very distinct issues that both have very different ways of solving them. This is important to understand because with scissors, there was really not a bottleneck other than the number of people I could get or obtain to cut my grass this way. But the real problem was the cost. And if I had the money to waste, I could literally waste money by paying a bunch of people to cut my yard with scissors. A bottleneck, on the other hand, can't be solved even if you have the money to throw at it. It requires a change to scale anymore. Unlike a cost scaling issue, a temporary fix cannot be just throw money at it. It fundamentally requires something to change. So if we look here at what the initial system was, we can see very easily that first there was this customer, some customer service, something that entered into this system that started a media conversion, basically converting frames into frames in S3, or converting a video stream into frames in the S3 bucket, where then a Lambda, I'm assuming this is actually the step function here, orchestrated parallel execution of these step functions that basically each one of them was scaled up to do some detection for some bad logic, dump that into these AWS Lambda result aggregation. So there's an aggregation system, and dump that into S3. And then all of these step functions could in fact call Amazon SNS, another service. Now, you'll notice that there is something a little weird here with step functions, and we're going to get into the step functions, but you can kind of think of step functions as Kubernetes operators for AWS built on Lambda. Each step is a Lambda function itself and passes around some state to subsequent steps. You can check that state and kind of figure out what you need to do. So step functions are a state machine on Lambda. It seems reasonable, but the devil is in the details. Always in the details. Now wait, you're passing around state? It's a state machine. What have we learned? How do you scale horizontally with ease? That is right, by being stateless. So step functions have some way of passing state. Who knows what that mechanism is, but this explains why it would be harder to scale something like step functions. Scaling stateful things is it's absolutely the worst, trust me. And let me be clear, who knows how Lambda works in the backend and how they implemented step functions on top of Lambda even at that. I don't have that information. I'm just talking about what we know from documentation and this blog post. Now, it's pretty complicated to know really what they are going to charge to use step functions, because not only do they charge you a standard Lambda function duration in gigabyte hours and by how many times your workflow is requested, but they also charge you for every state change. Anyhow, it can be kind of simply put as Lambda charges plus state transitions. For the most part, unless you call a bunch of workflows. But I think that would be really weird, although you could do that if you wanted, but it wouldn't scale very well. Now, these state changes that they charge you are actually pretty cheap on the surface. And if you use these state changes as I thought most people would, if you were to use them to orchestrate things like scaling events, it might only cost you 25 cents for 10,000 scaling events. That's very cheap. And as of recording this video, it was 2.5 cents per 1,000 transactions, or more exactly, it was 0.0025 cents per state change. This seems reasonable, and if you design a system where this only happens when scaling or retraining an ML pipeline or something like this, something you can plan on doing even up to the thousands of times per day, it's still dirt cheap. So what was their problem? Well, the root of the problem was how they designed it. Per their diagram here and their own statement, each video stream performed multiple state transitions for every second of stream. So let's guess, just guess 3 transitions per second, although I'm going to tell you that I think it's probably more. They don't state the average, but I feel like they would have used the word couple if they only made 2 transitions, but this really does not matter, as you will see in just a little bit. That means every minute of stream, it would be 180 transitions and then 10,800 per hour of video streamed. So for an hour of video watched, just the step function would cost you 25 cents. This does not include the Lambda gigabyte minutes and the workflow calls, but this is just for the for the state change. But this is just one stream. And we are just guessing at the word multiple, picking the lowest value. It could be more than 3 state changes, because if you look at their diagram here, they say that each detector had its own step function. And they also go on to say that there could be hundreds or thousands of detectors. So they could even mean by multiple into the hundreds of state changes. But we'll stick with 3 going forward. So at this, it would be 25 cents per hour per stream. So what would happen if you had 50,000 people streaming at once? Not a huge amount, I assume, for a provider like Netflix or Amazon Prime. Well, now it becomes about $12,500 per hour just for your state transitions. That is starting to get pretty expensive, as you would be looking at about $9.2 million a month for state transitions alone. None of the other things like gigabyte hours, workflow calls, or even the S3 buckets that we'll get into in just a second are included in that. Over $9 million just for state transitions. This does not seem to be the tool for their use case. That's all I can say here. And this is not even talking about hitting the hard limit of the number of states transition you could do in an account. Now, this is a good segue into, you know how I talked about cost and bottleneck being two different issues? Well, if it was only the bottleneck, let's say state transitions didn't cost you anything, but there was an upper limit of how many you could do in an account, they could have sliced this and made a second account, and this sounds very similar to how we scale other stateful workloads. This is just sharding your workload, and sharding is not bad. In fact, sharding is really at the root of most stateful scaling strategies, some type of sharding. And this is in fact something that they are going to do anyways to solve the bottleneck, as you will see in just a little bit. This is why I said bottleneck scaling and cost scaling were two different issues, and they are solved two different ways. Again, if there was not a cost problem with the step functions, they could have scaled the step functions by sharding. But that's not the case here. This tool, step functions, in fact has both issues, cost and bottleneck. Again, this is why being an engineer takes work, takes time, takes problems thinking, problem solving, good English abilities as well, and it really takes understanding how you might solve it. Now, this does not mean the tool is bad. To be honest, it's not a tool that I use, and so I'm not going to dive into AWS step functions or have the audacity to say they are bad. My point is, from the information here, all we can really say is that step functions were not the right tool for the job. They were not designed for something that runs 150,000 state transitions per second. That is how many they would be running with 50,000 streams at 3 changes per second. That's really crazy. State is expensive to transfer. Okay, so takeaway number 1. Step functions were not the tool to use when you could want to do hundreds of thousands of state and workflow calls a minute. It's just not the tool. Let's move on to the second problem. The next one has to do with transferring state between services and the cost it incurs. Again, they were storing all of this in S3. As you can see here, every single frame went into effectively an S3 buffer. Again, this was at AWS's fastest, highest tier of storage. This was a stream needed to be real time. So that's a lot of fast reads if you think about it, because each detector would need to read that one frame for every detector that was spun up. So if you had 100 detectors, that would be 100 high-tier reads for a single stream per second. So again, maybe this is not the right way to use S3. Does it mean that S3 as a tool is bad? Not at all. S3 has solved a lot of problems and is a pretty good tool. So at this point, all I have seen is know the tool that you're using, what problems it solves, and how to leverage said tool. It does not even matter if it was S3 or some other tool, like Linux. Transferring that much information between services is going to be expensive, and it is something you have to think about when you are designing your services. The flow of data is so important. Generally, a good rule of thumb to follow with microservices is that each microservice owns its own data, meaning you don't pass around its data and you don't transfer state. Sure, some other microservices might need some data, but that doesn't mean all its data. If you are passing around all its data to hundreds of other services that have the same goal, you might have a microlith. Also, I'm not hating on the people that made this. I hope that you know that. They did not design it to scale initially. It was a tool someone made and it worked the way they needed it initially. Then the requirements changed, as they often do, and it didn't work anymore. And I think they learned a lot of good lessons scaling it, which we can learn from. Now, on to the good part. On to the part I think AWS would even agree with me they got completely wrong. From distributed microservices to a monolithic application. I'm sorry. Let's start by looking at what AWS itself states as a microservice. Characteristics of a microservice. Autonomous. Each component service in a microservice architecture can be developed, deployed, operated, and scaled without affecting the functioning of other services. And then, specialized. Each service is designed for a set of capabilities and focuses on solving a specific problem. And the fact is, I don't see anything in this article that suggests otherwise. Do you? The service is in fact still quite specialized. I'm not saying that you could not break it into smaller pieces, but again, that is pretty true about just about any microservice, and you should really stop making extra services you don't need to. That is breaking everything apart to the extreme and generally leads to Lambda, not my favorite. I think people confuse holding state and a service architecture. Most microservices actually have state. They just store it in some database that the microservice owns. Is their new microservice stateless? No, it's not. But that does not mean that it's not a microservice. Notice anything about being stateless on the definition of a microservice? I don't think so. In fact, step functions themselves keep state. So if you were saying stateless was a requirement for a microservice, you would be saying step functions themselves are a monolith, and using them would make you a monolith anyways. So they were already a monolith by that definition. So I don't think we can take that definition. Not only that, if you think along the lines of team lines, as I do so often, as microservices really are a way of structuring teams, there is nothing to state that two teams shared the same service or code. In fact, the article is worded in such a way as to state that this is a single team that owns this service, meaning not only did it maintain, in AWS's own words, its autonomous nature, able to be developed and deployed independently of other teams, but it also maintained its specialization to detect bad video frames. That's what it did. That's the service. So, per AWS's own word, I would contend that this statement here, from distributed microservices to a monolithic application, is just incorrect and wrong. I would like to take a moment right now to ask AWS to clarify this blog post and update it, explaining more if that's what's needed, or rewording it to be more clear as to what they mean. I think that this blog article has actually done a lot of harm in the industry by releasing the article as it is. The current level of confusion around microservices is outstanding, and AWS is now adding to the problem. And you know what is even worse than that? ChatGPT is using this article as we speak to be trained to mislead the next generation of software engineers. So I would contend with the information provided here, not only did they not defend their statement, but that they are still following a microservice architecture with just a little bit bigger of a detection application. Remember, microservices does not mean that you just use Lambda or serverless or whatever the news buzzword is for the day. It's not a fashion trend, and it's not even a technology. This is not only wrong and incorrect, but you risk missing the true benefits from your architecture, and in understanding why you should use one architecture over another. Without this understanding, as an engineer, you will end up designing by the latest fashion trends and have very little real understanding of your architecture and why it's good or bad. Eventually, if you keep going this way, you will have a system you can neither maintain nor support as a company. Now, looking at this diagram, I would have sharded it differently than they did, because I think it would have kept state a little bit easier in the flow through their application. But I don't know everything about their application. They sharded by detector. I would have sharded by video stream. But you know what? They're smart people. There is probably something about their system, about their application and how it works that made sharding this way better. I honestly don't know, and I don't have any inside information on it. But look at this diagram. Does this not scream microservice to you? Let's take a look at it. We have some customer with some customer service, probably not Cognito because I don't think anybody uses Cognito. We have this media converter, an orchestration layer. This media converter looks like it can be developed and deployed independently. The customer service, the user service probably can be developed and deployed independently with its own thing. Orchestration seems to have its own service that is specialized to orchestration, can probably be developed and deployed independently. There is a detection service that detects bad video frames that can probably be developed, deployed independently, and is specialized. We have result aggregation service. This is probably still Lambda. I don't think that they actually go on to say that, but it's probably still a Lambda aggregation. We use AWS SNS, which is another team for notifications, which can be developed and deployed independently. I think you see where I go here. We're still using S3 for results, so we're still putting all of these detection results in S3, which is another service that can be developed, deployed independently, that is specialized to do one thing and do it well. What does this sound like to you? To me, it sounds like a service architecture, microservices. It doesn't sound like a monolith to me. Does their detection service detect for more than one type of failure? Yes, it does. And this is beautiful. Don't think that you can't do this in your microservice architecture. It's fine. Really, we've gotten to this point where we think we have to split it into a single function for it to be a microservice or a function. This is not true. You can have a specialized service that it's doing one thing. It's detecting bad video frames. That's what it's doing. You don't have to have 1,000 microservices that detect different types of bad video frames. Unless if you have a team, 1,000 teams. If you have 1,000 teams, I might contend that each one detects video frames differently, but they don't. And so that's not the microservice you need. I have a question. Before we wrap this video up, before we run conclusions, have you liked this video so far? Could you hit the like button and subscribe so I know to keep making video content like this? If you do, it lets me know that you like the content and want me to keep making more so that I know. Hit that like button if you're liking what you have heard so far, and if you'd like me to continue doing these a little bit more unorthodox response videos where we might learn from stuff that people post. So let's get back to this. What have we learned? What have we gleaned from this article? What tool you pick, whether it's a language you write your application in, your cloud provider, your architecture, your planning software, maybe Jira, or even your office, whether it has scissors or not, every single tool has pros and cons. Every tool should be designed to do something well, and it probably means it even doesn't do some things well on purpose. Just like a mechanical engineer will trade weight for cost or cost for weight in what material they pick to build something out of, or a civil engineer might pick different materials to build a road out of, depending on the structure of the ground or the shape of the dam. Every engineer needs to pick the right tool for the job, leverage it to its fullest, and know when not to use the tool, even if it's your favorite tool. Understanding a tool's weakness is the most important part. When you understand the weakness of a tool, you can then leverage it to its fullest as you know where it's going to fail you, when not to use it, or how to compensate for its weaknesses with other tools. I hope you all learned something. I hope you found this video entertaining and informative, but if you did not like this video and don't like thinking critically about the things you read on the internet, I'm going to need you to hit that subscribe button, stick around, and learn how Facebook is not for you. Long live the scissor architecture.